All right, everybody, we'll get started. A little bit slightly different. We do have cookies here, although it's almost a box per cookie, or a box per person of cookies so far what we have. So we'll have to see if we can get some, I'll adjust whatnot maybe in the future, but that or I'll just have lots of cookies to enjoy. We'll have a little bit different thing here, joined by Dr. Lenny Smith, who is teaching the special session or special topics course in ECE, the nonlinearity and prediction. I'll turn it over to you to describe more on this course that you're teaching on the phone.
Yeah, I mean, we'll put up an ad for this eventually. It just got approved, but it's a nonlinearity and predictability. If you were allowed a few more letters, it's really sort of everything I wish someone had told me about modeling when I was a graduate student. So it's really not so much about the mathematics behind models. It's more a question of when to use them and how to use them, or even when not to use them, as opposed to how to make sure your integration scheme converges. So there are lots of examples, and a lot of the examples you can actually bring in yourself. I can do balloon flights and ensemble weather forecasting, but I don't yet have nitrogen in the ionosphere. So come try it out.
So yeah, so that's for, I guess, for graduate students, it's limited to graduate.
That's right. For graduate students, there's still a 4,000 level, not yet approved, but there'll probably be a parallel 4,000 level, the same room in the same course.
Okay. Is it just for the ECE option?
No. It's for, so it's going to be co-listed with statistics. It's for, in fact, people in AOE suggested I mention it here.
Good.
So it's really for everybody. And yeah, don't worry about the maths part. Basically, I'll tell you why the undergraduate maths you were taught, it doesn't really work.
Okay, that sounds good. Thank you very much.
Thank you.
So we'll stop sharing that. And Srimoyee, if you want to share your presentation today, we have Srimoyee, who's a graduate student here, still in the ECE department, correct? And being advised by Dr. Bailey. So without further ado, I've forgotten the title already, but I do know, as I've gone on about, it's about nitrogen in the ionosphere, and for what I remember about the process of creation and
photoelectrons.
Yeah.
And dissociation of nitrogen.
Yeah. So yeah, without further ado, I'll let you take it away.
Thank you. Okay, so the topic of my talk today is the effects of high energy photoelectrons in the dissociation of nitrogen in the Earth's ionosphere. So these are the topics that I'm going to cover. Firstly, I'll talk about the solar spectrum and solar flares. Then a brief introduction to the thermosphere-ionosphere system. Then what are soft X-rays and photoelectrons. Then I'll talk about how we model the solar spectrum, how we get the ionization energy, the ionization profiles. Then I will talk about the photoelectron model, the NRL flare model, then how I get the photoelectron cross sections, how we update them. And finally, I'll talk about the ionization, excitation, and dissociation of nitrogen, and then how I get the nitric oxide profile from the dissociation of N2. So this is this plot is a very general solar spectral irradiance model. On the y-axis, you have the spectral irradiance, and on the x-axis is the wavelength. As you can see, the wavelength varies over like 10 orders of magnitude, and the spectral irradiance is almost 20 orders of magnitude. So there's a lot of variability here. So the soft X-ray is a part of the spectrum, is the radiation below 30 nanometers. Next, you have the UV, which is from 30 to 120. It's the extreme ultraviolet. This part is very variable. This comes from the solar corona, which is the outermost layer of the Earth's sun's atmosphere. And then there is another important part in the radio frequency range. This also varies a lot. with the sun's activity. And there's a particular emission, which is the 10.7 radio flux. This actually, we use it as a proxy in generating solar spectrum. So that I'll talk about it later. So like I was saying, the sun doesn't behave the same way from day to day. It varies. Sometimes the sun is very quiet, there's no activity. But sometimes, like now, there's a lot of activity. There's an event which is called solar flares, which we hear in the news now quite a lot. So that is basically a very high radiation that is emitted from the sun, and that is in the soft X-ray range. And based on the strength of the radiation, we can classify the the solar flares in different classes. So here is one example. The M and the X class, these are the strongest flares, and these can cause radio blackouts or radiation storms in our atmosphere. So now I just talk about our Earth's atmosphere. There are basically 4 layers in our Earth's atmosphere: the troposphere, stratosphere, mesosphere, and thermosphere. The way we divide it is like according to the temperature gradient. So in the troposphere, it starts from the sea level, goes up to around 10 kilometers. The temperature decreases over here. Above that, we have the stratosphere. You can see the temperature is increasing. Mesosphere starts at 50 kilometers. Temperature decreases again. And then you have the thermosphere, which starts around 90 kilometers. And here I've plotted a temperature profile above that 90 kilometers. So as you can see, the temperature is increasing up to like 250, and then it kind of levels up. So that's why we call it a thermosphere. So now I talked about what the sun is doing, our Earth's atmosphere. How are these two related, and why I'm talking about that is because most of those X-ray and the UV radiation coming from the sun is absorbed in the thermosphere, and they create the ionosphere. Ionosphere is not like a different layer. It's basically embedded in the mesosphere and the thermosphere. So when these soft X-ray and the UV radiation are absorbed, particularly in this E layer of the thermosphere, they ionize the neutral species in this layer. And here I have shown an electron density profile. So when an ionization happens, you get electrons. So when the soft X-rays and the UV radiation create these electrons, we get these electron density profile. So this is a typical electron density profile. The red line is for daytime, and blue is the nighttime. So as you can see, during the day, this D region electron density is quite enhanced. And the E region, there's a peak electron density over here. However, when the night comes, you don't have these sources of radiation. Recombination takes over. So now you can see the electron density in the D region almost vanishes, and the E region peaks goes down. So that is basically what the soft X-ray and the UV radiation are doing. They are ionizing and creating the ionosphere. So now how does the soft X-rays and the thermosphere, how do these relate? So the soft X-rays, they ionize the neutral species and they create photoelectrons. So what are the neutral species? The main neutral species in the thermosphere is the N2, O2, and oxygen atom. And it's creating a photoelectron. And what these photoelectrons do is they have very high energy, and they can cause secondary ionization, excitation, and dissociation of molecules. So this is an example. So when the photoelectron, which is the E star, it's hitting the nitrogen molecule, it's ionizing the nitrogen, and it's creating another secondary electron. Or it can excite the nitrogen into a higher energy state, this N2 star. Or after this, there can be another process which leads to the dissociation of this N2 plus into fragment atoms and ions. Or this excited nitrogen can also dissociate and it can create fragmented nitrogen atoms. These nitrogen atoms react with the O2 molecule in the thermosphere and they create nitric oxide. And nitric oxide is one of the most important minor constituent in the thermosphere. And in this study, I'm basically concentrating in this, what the soft X-rays are doing, how it's creating the photoelectrons, how it's the photoelectrons are ionizing, exciting the nitrogen molecules, how the dissociation process happens from this ionization and excitation, and how nitric oxide is formed. So this is mainly the composition of our Earth's atmosphere. As you can see, nitrogen is the main species, 78% nitrogen. And in the minor constituent, right at the bottom, we have nitric oxide. It's less than 1%. But it's a very important minor constituent because it's a very important source of cooling in our thermosphere by this process called radiative. It's a radiative de-excitation. So when there is some high energy source, this nitric oxide, it's in a higher excited state. So it can radiate this 5.3 micrometer emission and it can go to its ground state. And this is a source of cooling. So nitric oxide is actually behaves like a thermostat. Secondly, this process of photoionization of nitric oxide by Lyman alpha emission, it's a very important source of NO plus, and this basically creates the D region that we saw before in the D region of the ionosphere. Thirdly, nitric oxide, it's very easily ionized, so it controls the ion composition of the E region of the ionosphere. And nitric oxide in the polar region can actually travel down to the lower altitude and it can catalytically destroy ozone. So that's why it's a very important minor constituent and that's why it needs to be studied. So I was talking about the solar soft X-ray radiance. This is a figure of all the measurements that have been done by various instruments throughout history. It's from 1998 till 2015. These are the different instruments. The last one, this light blue F10.7, that is a modeled spectrum. The main takeaway from here is there is a lot of inconsistency in the data, the soft X-ray data. So which leads to a lot of inconsistency in modeling the thermospheric temperature or the nitric oxide density. So that is another motivation for studying the soft X-ray radiance. So how do we model the solar spectrum? This is a very typical solar spectrum. This is called the UVAC empirical spectrum. This is basically a histogram. So you have the wavelength in the x-axis and the solar flux in the y-axis, and the solar flux are put into wavelength bins. And the way this solar spectrum is generated is by using this F10.7 that I was talking about before, the F10.7 centimeter radio emission. So this p-value is the average of the F10.7 daily and the F10.7 81-day average. And depending on this, it gives you kind of the solar activity. So if you have a small p-value, that means the sun is quiet and you will see that the solar flux is less. And when the p-value increases, the solar flux becomes more, particularly in the soft X-ray part of the spectrum. It almost increases by 1 order of magnitude. That's how this UVAC model generates this solar spectrum. So like I was saying, most of the energy of the soft X-rays are deposited in the lower thermosphere in the E region. This plot actually shows the contribution from the soft X-rays. So I have used the same UVAC model that I showed previously, and I have changed the p-values from 70 to 265. So 70 is for low solar activity and 265 is for high solar activity. And so this shows a box plot. So the y-axis is the ionization percentage ionization energy, and I have divided the UVAC spectrum into 3 regions. So anything less than 30.4 nanometer is the soft X-ray part. Then I have the 30.4 nanometer, which is the strong helium emission that it's from the radiation from the sun. And then everything above 30.4, I have put it in this box. So in the E region, you can see 65% of the ionization is due to the soft X-ray. But if you go to the F region, that is higher up, 300 kilometers, the contribution from the soft X-rays is like 25%. And most of the ionization is happening due to the EUV form. So that's why I'm concentrating in the lower region of the thermosphere, like below 200 kilometers, because that's where all the actions from the soft X-rays are happening. So now how do we generate an ionization profile? This is a very typical ionization profile. This is an ionization profile of nitrogen. So on the x-axis, you have the photoionization rate, and this is as a function of altitude. This ionization was generated using this UVAC solar spectrum and for a quiet condition. So F10.7 is 70. If I increase the F10.7, so higher solar activity, you will see that the lower region, like 100 kilometers, this part will get enhanced. Another important parameter, which I'll talk in detail later, is the cross-section. This cross-section is important to generate the photoionization rate. So for the photoionization of N2, I will need the photoionization cross-section, and this plot is a typical photoionization cross-section. On the x-axis, you have the photon energy, and the y-axis is the cross-section. So now I've talked about the basic theory of soft X-rays and the thermosphere. What are the science questions that I'm trying to answer through modeling? Firstly, what is the effect of the high energy photoelectrons that are created by the soft X-rays during flares? And this I'm going to study using this NRL flare model. Secondly, how does the uncertainty in the electron impact cross-section data impact our calculation of the dissociation rates of nitrogen? This I will talk about the photoelectron cross-section and how to use the photoelectron model. And lastly, I'm going to use the updated photoelectron dissociation cross-section and the dissociation rate of nitrogen to estimate the nitric oxide production. So first, I'm talking about the NRL flare model. So this is the NRL flare model. It's the same, it's an input spectrum where the flux is put into different wavelength bins. But this shows a flare. So this flare is the X9 flare of September 6, 2017. This dashed plot, that is the flare. And for this study, I have assumed overhead sun. And the F10.7 is pretty high over here. And to compare the X9 flare with a quieter condition, I have generated this white spectrum from this X9 flare by basically reducing its amplitude by various orders of magnitude in different spectral bands. And I also have assumed an F10.7 of 70. So now the photoelectron model, which I'm going to use to calculate all those dissociation rates. So what the photoelectron model does is basically it calculates the photoionization, the photoelectron ionization, and the photoelectron dissociation rates of various species. The input will be the high resolution NRL flare model and the recent electron impact ionization and excitation cross-section data. And this is the basic equation that controls the production rates. So Qi is the photoelectron, the process rate. So ionization, excitation, dissociation, whatever rate you want to calculate. the phi is the photoelectron flux, E is the number of energy bins, Z is the altitude, delta E is the width of the energy bins, and this one sigma I is the photoelectron cross section, and Ni is the neutral densities. So in this model, there will be uncertainties, and that's what I'm going to study. So first, I talked about the inherent uncertainty in the solar flux data, which is present, especially in the soft X-ray range. Secondly, this sigma I, which is the electron impact cross-section, there's a lot of uncertainty in the data itself, and there's also data is very scarce, so there will be uncertainty there. And finally, the dissociation rate, I'm going to use for the dissociation rate, I'm going to use the electron impact excitation cross-section, and I'm going to derive the dissociation cross-section using this something called the predissociation factors. And there will be uncertainty here, and I'll go through each of them. So for calculating the dissociation rate, I'm basically considering two important processes which leads to dissociation in N2. First one is the electron impact ionization. I've shown this before, but just to reiterate, this N2 is hit by the photoelectron and it's creating the N2 plus. And when this N2 plus dissociates, it gives you N plus and N. So this is one dissociation channel. The second one is from electron impact excitation, where the ground state N2 is transferred to a higher excited state, and this excited state can pre-dissociate and create nitrogen atoms. Now, this nitrogen dissociation I'm estimating from the excitation cross sections using pre-dissociation factors. So why I'm updating the electron impact cross-section data is basically the older models. The data is pretty old, the resolution is not good, and now we have higher resolution spectroscopic data. So that's one reason to update it. Secondly, nitrogen is it's a triple bond molecule, it's very difficult to dissociate, and these high energy photoelectrons can dissociate N2. So I need cross sections for these high electron energies, which are there in the present literature. Also, because of these high photoelectrons, the higher excited states of nitrogen, the photoelectrons can excite those higher excited states. And I have added those higher excited states, and those are very important in the excitation of nitrogen. And lastly, I'm adding these pre-dissociation factors to estimate the excitation cross-section, the dissociation cross-sections from these excitation cross-sections. And these are experimentally determined, which was not there in the previous model. So this is an example how it is done for the electron impact excitation cross-section data. So all these states are the various N2 star states. And the blue ones are the states which can pre-dissociate. And these have been experimentally determined. So this is singlet by G state. This is 12% dissociation. So all these have been updated in the present model. These are all the excitation states that have been updated here with their pre-dissociation percentages. This is a comparison with the older cross-section, which was taken from the Solomon Chen 2005 paper. It's called the GLOW model. And these are all the excited states of nitrogen. The last three in red, we assume that they dissociate. We do not know their dissociation. But in the present model, we updated all these states with their experimental pre-dissociation cross-section and also the higher resolution better cross-section. So after doing all those things, this is the final cross-section of nitrogen. And I've compared it with the GLOW model cross-sections. So the red one is the Solomon and Chen or the glow model cross section, that is the older one. The blue one is the present. So this one is the dissociative excitation of nitrogen. This one is the dissociative ionization, and you add these two, and this is the total dissociation cross section of nitrogen. So basically, we see that the present dissociation is 0.65 times the older the Solomon and Chen dissociation. Because there is so much uncertainty in the data itself, this is a good approximation and it is within the error limits of the cross sections. So that was all the inputs to the photoelectron model. Now I'm going to talk about what the results are. So, like I said, there are two dissociation mechanisms for nitrogen, the electron impact excitation and the electron impact ionization. So the dark blue is the electron impact ionization and the light blue is the electron impact excitation. So the maximum contribution to dissociation is around 85% for the excitation. And so most of the dissociation that is occurring in nitrogen is due to the electron impact excitation. So, and that's why it's important to update all those states, all those cross sections. So this is the plot of the ionization and dissociation rates of nitrogen for the X9 flare. This is an altitude profile. On the left plot, you have the altitude profile versus the rate. So the red one is the photoionization rate of nitrogen. The yellow one is the electron impact ionization rate, and the blue one is the electron impact dissociation rate. And on the right hand side, I've just taken the ratio of these two rates. So yellow one is the photoelectron ionization to the photon ionization, and the blue one is the electron impact dissociation to the photon ionization. So basically there are two important results. The first one is because I'm using this high resolution soft X-ray radiance data, I am basically able to get the resolve this or the altitude profile below 90 kilometers, which was not possible before. And that's possible with the higher resolution solar spectrum. Secondly, if you look below 130 kilometers, the photon ionization rate is not the main driving factor, but the photoelectron ionization rate. So it is almost, the photoelectron ionization rate is almost 300 times more than the photon ionization rate. So the solar photon is not really driving the ionization below 130 kilometers, it's the photoelectrons. And this is where we see the significance of the soft X-rays and the solar flares, because during the solar flares, the soft X-ray radiation is getting enhanced. It's causing more photoelectrons, and that the photoelectrons are really driving that ionization and dissociation at these low altitudes. These are the other species which the photoelectron model can calculate. I'm not going into too much details over here, but the first row is the same as the previous one for nitrogen. I've just added the quiet condition over here in the borderlines just to compare the effects of the flares. So you can see the effects of the flares are really pronounced at these low altitudes. Second important thing is because N2 is so difficult to dissociate, all the dissociation is happening is due to the soft X-rays and the UV, because they have sufficient energy to dissociate N2. However, oxygen molecule is very easily dissociated. It requires almost half the energy of N2. And so there will be other sources of dissociation of O2 besides the soft X-rays and UV, like the SRC continuum and all those things. But so I have not shown that here. So this is not the complete picture for dissociation of O2, but the model can calculate the photoelectron dissociation of these species as well. Another important thing is Now that we can resolve the altitude profiles below 90 kilometers, I can use these ratios, this photoelectron to photon ionization ratio and the photoionization in a parameterized version in any thermospheric model, and I can get the photoelectron rates. So that is an important output of this model. So since I updated the electron impact cross-section data, how did the dissociation rate change? This is an altitude profile for the photoelectron dissociation rates of nitrogen. Um, this is a comparison of the present and the older Solomon and Chen cross dissociation rates. So as you can see, the present and the Solomon and Chen, the ratio is 0.7 times. So the present photoelectron dissociation rate is 0.7 times the Solomon and Chen, which is very close to what we got for the cross section. It was 0.65. So it's a good approximation here. So now that I have the N2 dissociation rate, I can calculate the nitric oxide production due from this N2 dissociation. So for that, I'm using this ACE1D model. The ACE1D model is global average thermospheric ionospheric model. It gives you the global average density profiles, temperature, and all those things. And it for that, I have used two input spectra really, and I have kept the conditions same for the September 6, 2017. So this F10.7 is 140 and the 81-day average is 84, which is giving me a p-value of 112. So the solar spectrum that I'm using here is the NRL, but I have removed the flare effects from here just because it's a global average model. And the UVAC spectrum that I talked about earlier. So the NRL model, you can see that it has higher resolution below 1.8 nanometers. So the soft X-ray part of the spectrum, the resolution is increased, and UVAC is like mostly broadband over here in the soft X-ray. And on the right hand side, it's the same thing, but the flux units are different. It's in milliwatt per meter square. Basically, so that you can see the resolution in the soft X-ray clearly. This is the nitric oxide production that I'm getting from the ACE1D model. So the first one is the red one is the original ACE1D model. I have not changed anything. The blue one is where I've just updated the photoelectron cross-section data, the dissociation rates of nitrogen. And the green one is where I have increased the solar spectral resolution as well as the photoelectron cross sections and the dissociations. So on the right hand side, I just plotted the ratio of the these two models. So the blue one is the ratio of the this blue to the red original model, and the green one is this green to the original ACE1D model. So you can see that the difference is very less at the higher altitudes, above 120 kilometers. It deviates at the lower altitudes, mostly because that is where you see the effect of the binning of the soft X-rays, and that's where I've like really changed all the cross sections and the dissociations. But on a global average sense, this is a good approximation for the entire altitude profile. I could not resolve it below 100 kilometers because the ACE1D doesn't go below 100 kilometers. But I think there might be more difference if we can go low. So this is the conclusion. So I've answered the three questions. Firstly, what is the effect of the high energy photoelectrons created by the soft X-rays during flares? The high energy photoelectrons created during the flares are responsible for the dissociation of nitrogen at lower altitudes. Secondly, how does the uncertainty in the electron impact cross-section data impact the calculation of our dissociation rates of nitrogen? So the overall dissociation rates as a function of altitudes calculated during the two cross sections, they agree well, and they are within the error limits of the experimental cross section data that is available in literature. And lastly, what is the effect of the updated photoelectron dissociation cross section of N2 in the estimation of nitric oxide production? The nitric oxide from the N2 dissociation in both the updated and the original model, they agree well in the global sense, and they deviate at the lower altitudes. So that's the end of my talk. Thank you.
Just back down to myself, unfortunately, Dr. Lang said that had to go here in the middle. I'll open it up for any questions that anybody online might have. I don't see anything in the chat, but if you can't talk with us today or in a noisy situation, feel free to enter them in the chat. Otherwise, feel free to unmute and ask a question.
Srimoyee, from the perspective of the modelers, are your revised cross sections, do they help or hurt in terms of the community being able to use models to reproduce observed nitric oxide?
I think it helps because previously when I was looking at the cross sections, there is really low, there's almost no cross section data, but because of there have been a lot of experiments, particularly for nitrogen, where there are data available, the higher resolution spectroscopic data. And previously, there were lots of theoretical guesses with the cross sections. Even though like the differences are not that much, but we have experimentally, we have been able to confirm that those cross sections are correct or within their limits. So I think it's good. We also have like cross sections for higher excited states. Those emissions are important in the thermosphere. More and more experiments are being conducted to resolve those higher excited states. So I think it's good.
Okay, that's good. So what you're saying is you're helping the models, right, tie their their chemical reactions to reality, right? Their algorithms are more tied to reality because of the data you've introduced. But it's also true that historically the global models tend to predict less NO than what we observe. So in that sense, do the changes you're suggesting help that problem or hurt that problem?
I think it helps. I have, I mean, at least at the for the soft X-rays, I am the energy, the irradiance that I looked at, and I compared it with your 2002 paper, and it was a good approximation to what I was getting. At the lower altitude, I was getting a bit higher nitric oxide. So I think that's a good estimate, increasing, I mean, updating the cross sections.
Okay, I that sounds good. That's good. I have a trivia question for you, if it's okay.
Yeah, sure.
When you put those cross sections into the model, you use an analytic description of the shape of the cross section profile, right? You did a fit, correct? What famous scientists introduced us to that approach, the analytic description? Who came up with those expressions?
I mean, it's called the bond breadth approximation.
So that's an approximation for what the high energy part of the cross section should look like.
Yes.
That the equation to describe the energy, the variation with energy of the cross section, the fitting 5-parameter function. Do you remember who came up with that?
Green
Uh-huh.
and Samaddar.
Say it louder.
Samaddar, Sawada,
Uh,
Jackman, and all those people.
So Charlie Jackman, right? It was his advisor in graduate school. Do you remember the name of his advisor? So this is a trivia question. It's okay if you don't.
I knew it, but right now I can't.
That's all right. So Charlie Jackman may be one of the famous examples of this person's graduate students that he graduated. His name is Alex Green. So where I was going is, do you know who Alex Green's most famous undergrad research assistant is? I'll give you a hint. He's in the room with you.
Not me. The virtual room, right?
Well, isn't Lenny still there?
No.
No. Yeah.
Oh, darn.
Yeah.
Okay.
Yeah, so Lenny had to leave here.
Okay, well, sorry about that. Now it's not a little bit funny. It's only funny because I screwed it up.
No, that's okay. That's all right.
Mhm.
There you go. I had a bit of a question. I'm not sure if you mentioned it or whatnot. You compared this some real data from a solar flare in 2017. Was there a particular reason why you chose that flare versus any other flares?
So this NRL flare model, this one.
Yeah.
So this is actually a physics-based model. We don't really have that resolution like data. So I was working with NRL and we created this X9 solar flare. And I was studying the solar flares and their effects at the lower altitude. So I do have other data, but we were just trying to get the strongest flare we could possibly get.
Okay. Yeah, I think I am remembering that because one thing too, I thought maybe the answer might have been the sort of your third point there, where right in 2017, I think we were starting to get towards solar minimum, and so but I do remember there was that strange, like there was a really strong flare, even though we were not in the last solar maximum. Yeah, so it's interesting. Yeah. Okay. So just it being the strongest.
Yeah.
Okay. Cool. Any other questions? Maybe one last other simple one. Sorry, towards the end of your conclusion, you're saying the updated cross sections end up increasing the nitric oxide at the lower levels,
Yes.
like at lower altitudes. Does that seem? I guess is there any research that kind of corroborates or kind of supports that kind of thing? That where you've seen where traditionally before. There was some kind of disconnect where models were saying that it was this value, but measurements maybe said it was a different value. Is there anything that kind of gets it closer down to real data?
So I was looking at Dr. Bailey's 2002 paper, and I was just trying to infer whether the model was giving me correct values.
Okay.
So he has it for different. There's a plot where he compares different solar, like he changes the solar flux in the soft X-rays, and he compares the nitric oxide, correct? And the total irradiance in that I think it's 2 to 7 nanometers. I tried to keep that total irradiance in that 2 to 7 nanometers almost like same like the UVAC model would give, and I tried to estimate the nitric oxide through that, and I compared whether that kind of correlates to what the 2000 paper was giving for that area.
Okay.
If that makes sense.
I think I sort of Well, this is all sort of
Yeah, I was-
definitely new to me, so.
Yeah,
Yeah.
I haven't like really gone into the details of nitric oxide, so I was just following that paper, and it's basically the snowy observations. So it's just,
Yeah, I'd say, I guess it's just saying, you come up with, updated cross section and then kind of rerun things. And just wondering if that, kind of gets us closer more to realities.
One way to look at that, Srimoyee, is most of your work changes things at the highest energies, the shortest wavelengths, right?
yes,
And where does that deposit?
at the lower altitude.
Yeah, if there's not any other questions, I'll maybe give it just a brief pause. Thank you, everybody, for joining. Again, this is the last one for this academic year, with the semester ending in just a week's time. Although I am starting to see we might have a bonus one, bonus seminar coming up in May. That's a date to be determined. So I'll send out announcements when we have that available, and hopefully people can join for that one as well. But otherwise, I want to thank Srimoyee for today, and as well as all of our speakers that we've had through this semester and this year. Everybody have a good last week and into finals for those who are involved with classes either on the student side or on the professor side as well. I know it's a small feat for doing finals. With that, thank you very much, and we'll see you, I guess, in the bonus one or maybe any other ones over the summer, or if not, into the fall semester. So.
Kevin, I want to thank you for the good job you did all year keeping this running. We all really appreciate that.
Yeah, no problem. No problem. It's been really good. It's been good to hear everybody, all the different things going on around the center. So.
Yeah, all right, well, great. And Srimoyee, you did a great job today, right? Very good seminar.
Thank you.
All right. See y'all later.
Thank you.